Hello everyone, welcome to chapter 7. From this chapter, we are diving into energy and energy balances. In this chapter, we're gonna learn component of total system energy, the difference between heat and work, definition of closed system, open system, isothermal system, and adiabatic system. You will hear these terms a lot in your chemical engineer career. And then we're going to learn how to write energy balances for closed system and open system and how to calculate unknown variable using this energy balance. Conservation of energy is just like conservation of mass that we talk about in chapter 4. The first law of thermodynamics states that energy can neither be created nor destroyed. Energy can only be converted or transferred. It's an interesting story that every Saturday afternoon I go to my local fitness center. My coach always say that let's create some energy today. I never correct him that based on first law of thermodynamics, energy cannot be created or destroyed. Now back to the slide. The picture on the left is a popular billiard ball game. When you hit the cue ball, the ball will strike another. While this occurs, energy is being transferred from the cue ball to another. Hopefully the target ball will get into the pocket. The picture on the right is an old steam chain, while the steam engine converts thermal energy to mechanical energy so the chain can run. There are three elements in the system energy: kinetic energy, potential energy, and internal energy. Kinetic energy is the energy due to the motion of the system in terms of mass and velocity. Potential energy is the system due to the position, or we can say elevation of the system. Internal energy is due to the movement of the molecules within the system. In other words, it's the energy of the system other than kinetic energy and potential energy. Putting them all together, we have this equation where the total energy within the system is equal to internal energy plus kinetic energy plus potential energy. Now let's look at each energy term in detail. Kinetic energy with the symbol E sub k or E dot sub k is the energy due to the motion of the system in terms of mass and velocity. The equation used for kinetic energy is 1/2 times mass times velocity squared. SI unit for mass is kilogram, and velocity, I use the symbol U to differentiate with volume. Is the velocity of the mass m relative to the surface of the earth. SI unit for velocity is meter per second. Then we'll get unit for kinetic energy is kilogram meter square per second square. That is also equal to Newton meter. That is joule. Joule is the SI unit for energy. We can also replace mass with mass flow rate. Remember, mass flow rate is the change in mass per change in unit time. Then using mass flow rate to describe kinetic energy, we have units of joule per second. That is watt. Potential energy with the symbol E sub P is the energy due to the position of the system. The equation used for potential energy is the mass of the object times gravity times elevation of the system. For example, a giant rock on top of the mountain will have very large potential energy due to its mass and position on the mountain relative to the bottom of the mountain. Potential energy had the same units as kinetic energy because mass is in kilogram and gravitational acceleration has a unit meter per second square. Then we have the unit is kilogram per meter square per second square. That is Newton meter. That is joule. Again, we can replace the mass with mass flow rate. Then we have the units joule per second. That is watt. The internal energy with the symbol capitalized U is the energy due to the movement of the molecules within the system. Let's use a warehouse as an analogy. In the warehouse, every worker is like an individual molecule within the system. All the workers are doing their jobs. Some workers are loading, some workers are packing, and some workers are discharging goods. The total energy caused by the movement of these workers inside the warehouse is just like internal energy of the system in micro scale. We will talk about how to calculate internal energy later on in this chapter. Energy can be transferred to or from the surroundings. When energy is entering the system from the surrounding, then we say energy is added to the system. In this way, energy is positive. When energy is leaving the system back to the surrounding, we say that energy is removed from the system. In this way, energy is negative. There are two ways to transfer energy: heat and work. Heat is energy flow due to the temperature gradient. In the textbooks, the symbol for heat is capitalized Q. Some books also use lowercase q. Either way means heat in this course. When it's written as Q dot, that means rate of energy transferred by heat. Flow of energy is from high temperature to low temperature. And why is that? Well, because the molecule in the hot region move faster than molecules in the cold region. And think about when you heat up an area or heat up something, molecules expand and they will diffuse to somewhere with more space in the cold region. In another word, heat is the diffusion of energy. Remember, heat is only transferred when there is a temperature gradient. If the temperature is the same, we say it's at thermal equilibrium, then there is no energy transfer. When I was little, we spent Christmas Day at my grandparents' house. My cousin and I ran in and out of the house without closing the door. My grandma always yelled at us, "Don't let the cold air come in." Well, now that we learn heat flow only from high temperature to low temperature in one direction, it's not the cold air coming, it's the warm air flows out. Alright, when the heat is transferred from the surrounding to the system, then we say that heat is added to the system from the surrounding. In this way, heat is positive. On the other hand, when heat is transferred from the system to the surrounding, we say that heat is removed from the system. Then heat is negative. Just remember, whenever energy is removed from the system, it has a negative sign. Whenever energy is added to the system, it has a positive sign. Another way to transfer energy is work. Work is the energy flow as a result of any external driving force other than temperature. Well, because we say if the driving force is temperature, that is heat flow. Example for work like torque, voltage, friction. If you take the course thermodynamics, the first day in the class your professor will ask you to explain work that you learned from PCP. Well, just remember, work is driven by external force times the distance moved by this force. And mathematically, we can write this way: work W is equal to F dl. dl is the distance moved by the force against the movement of the system. There are two types of work in this course that we're going to talk about: shaft work and boundary work. In the textbook, it also mentions flow work, but we mostly focus on shaft work and boundary work. Again, when the surrounding does work to the system, we call it input. Then work is positive. When the system does work to the surrounding, that is output. The output work is negative. Shaft work with the symbol W sub S, S is for shaft. Shaft work is the mechanical work done by the turbine or the pump, because in the center of the turbine or pump there is a shaft. It causes a rotational movement. That's why we call it shaft work. The turbines we usually see are wind turbine, steam turbine, hydro turbine at hydroelectric dam. Jet engine is also a turbine. Another work is called boundary work. While boundary is the surface that separates a system from the surroundings, it may or may not be a real surface. It can either be a rigid or a movable surface. Boundary work is done by an external pressure exerted by the system at the boundary, causing the system to expand or compress. Because we say that work is FDL, F is the pressure force in this case, times the impact area. Remember, the pressure force is always perpendicular to the impact area. Then area times distance is volume. Then we can describe boundary work as PdV. Because we have said many times when the work done by the system is negative, so let's put a negative sign in the front in this equation to keep it consistent. In this way, when the system is expanding, dV is positive. Positive negative is negative because we say work done by the system to the surrounding, that's negative because dV is positive and negative work is negative. When the work is done by the surrounding to the system, causing the volume to decrease or compress the system. In this way, dV is negative. Negative is positive. Then we have a positive work that is input caused from the surrounding on the system. That's how this negative sign in the boundary work works. Now, let's put all the equations together. The total system energy is the sum of energy being transferred. On the left of the equation is the system energy, and we say there are three components in the system energy: kinetic energy, potential energy, and internal energy. On the right of the equation, that is the ways to transfer energy, which is heat plus work. That's shaft work and boundary work. The change in system energy is the system energy in the final state minus the system energy in the initial state, which is equal to the sum of energy being transferred. You can either write in this way using delta sign in the final state minus initial state, or can write in derivative term d energy over dt. That's energy change with respect to time. Do not matter in the equation as long as you have all the components of the system energy on one side of the equation and the way of transferring energy on the other side of the equation. Thank you for watching my video. If you like my video, please subscribe to my channel, or you can buy the whole course from my Udemy link. Good luck with your study!